Hi, everyone. This is Julia from the Macedon Public Library, and we have another science talk today about space ghosts. So without further ado, let me pass you along to Brian. Here he is. Oh, with his notes.
With my notes. Got to be proper with this, right? So I thought I would talk about, you call them ghost particles. They're formerly called neutrinos. So they're a fundamental particle. If you think of, say, an atom, there's protons and neutrons in the nucleus of an atom, and then there are electrons that orbit that, if you want to say that. And protons and neutrons are made up of strange particles called quarks. We're not going to talk about those, but electrons are things that are just electrons. They're not made up of anything else. They're what we call a fundamental particle. And so for a long time, it was thought that protons and neutrons and electrons were the only things that everything was made up of. And in the 1930s, they started to understand how these particles interacted. They could do experiments called particle physics and do this. And when they started studying them, they found that the energies of the particles didn't add up. So basically, if you had something like uranium or strontium or something like that, something that was radioactive, you could watch it decay, and if you counted up all the energy of all the particles flying off when it decayed, it didn't add up. And they couldn't see that there was this, somehow there was something that wasn't adding up with the energy. And when they studied it further, it looked like there was some particle that couldn't be seen that was taking some of the energy. And Enrico Fermi called them little neutral particles because they couldn't have a charge, otherwise we would see them. Called them little neutral particles, or neutrinos, which is where the name comes from. So neutrinos were first discovered in this early stage of the 30s of particle physics. And the reason they were so mysterious is that they're very, very difficult to detect. So if you think of electrons or electric charges and things like that, things that we see in electricity, the electric force is a very powerful force. And so things that have an electric charge can actually have a big result. This is why you can rub your feet on carpet in winter, and then if you touch a doorknob, you get a spark. Because all you've done is just rub your feet together, and all of a sudden you get something you can feel, you get something you can measure. And that's because things that have electric charge interact with each other very strongly. So light interacts with charged particles, and charged particles interact together. And so most of what we see in our everyday world is due to this electric charge. So that's why we can see things. That's why things feel solid, because the atoms are held together by an electric charge. When they bond together, they create this force that's hard to push. So that's why we have solid objects. And neutrinos don't have any electric charge. They don't interact with charged particles. And so if you think of an atom as being this very tiny nucleus and then this cloud of electrons around it, if something has charge, it hits the atom and interacts with it. But a neutrino doesn't interact with the charge of electrons. So neutrino basically goes right through all the atoms. So like right now, there are billions of neutrinos streaming through you, and you don't notice it because they just go right through. So the only time you can actually see the interaction of a neutrino is if it happens to hit the nucleus of the atom. So if it hits the nucleus of the atom, then it can cause the atom to do all these different things. So in order to detect neutrinos, what we have to do is we have to have these large chambers of lots and lots of things. They're the size of room or a house in terms of how big they are. And it's either something like water or a sheet of a special kind of plastic or ice in Antarctica, but you have to have these huge detectors just to detect neutrinos. And what you're doing is you're having such a large detector that, well, the odds are that as neutrinos stream through them, they'll hit some of the atoms and then you'll be able to detect them, because most of the neutrinos are going straight through and you never see them. The other thing about neutrino detectors is they have to be buried underground, because in order to detect the neutrinos, you have to detect one of these little neutrino particles striking the nucleus of an atom, which then causes the atom to give off a very, very tiny bit of light. And lots of other things could strike the atoms. If you had them just in your house, ordinary electric fields, the light from that would strike the atoms and create light. And so you have to bury them deep underground. So neutrino detectors are typically in mines deep underground. I've actually been to one neutrino detector in northern Minnesota that's in an iron mine, and it's about half a mile underground, surrounded by iron ore. And it has to be that way to shield it from things like cosmic rays and electric fields and all of that. And so they're typically buried deep underground. There's one in Japan that's a water one that's based with heavy water, and so it has a very big chamber. And then there is one in Antarctica where they actually just dug into the ice of Antarctica. So they're about a half mile under the ice, and they just put an array of detectors, and they use the ice as the material that detects the neutrinos. So we have them kind of all over the world in various places, but they're very hard to detect neutrinos. So that's why they're sometimes called ghost particles. They're also sometimes called ghost particles because they're spooky. They behave in very strange ways. So one of the things is that neutrinos come in 3 different types, and they're called flavors. So they come in 3 different flavors. And that by itself is not unusual, because lots of things come in flavors. So electrons that we are normally familiar with, it turns out that the electron is one flavor of a type of particle called a lepton, and there's 2 other types. There's a muon type that is like a heavier version of an electron, and then there's a tauon type that's like an even heavier version of an electron. And we don't see them every day because you have to have a lot of energy to produce these different flavors. Okay, but an electron, if you make an electron, it stays an electron because it's just an electron, because it's an elementary particle. If you make a muon, a different type of electron, then it just stays a muon. So they stay the same type. Neutrinos don't. So neutrinos come in 3 different flavors or 3 different types, and they can just switch from one type to another. It's an effect called flavor changing. And neutrinos are the only particles that do this. They change flavor. So it's kind of like if you got a bowl of vanilla ice cream, and by the time you brought it to your lips, it was chocolate. And then you pull it away from it and you look at it, now it's strawberry. It doesn't follow common sense, but this is what neutrinos do. So they're hard to detect. They do this weird changing of flavors and stuff. And we don't really fully understand them yet because they're hard to study. So they're these spooky, ghosty particles that are streaming throughout the universe that we'd have to spend a lot of effort just to detect some of them. So that's kind of why they're ghost particles. But the interesting thing about neutrinos is that the more we've studied them, the more they have told us about how the universe works. So one of the things that produces neutrinos, as I've said, is the radioactive decay. So radioactive elements like uranium, when they decay, they give off a lot of things, but one of the things they produce is neutrinos. And so we can produce neutrinos in fission reactors. So we can actually have a nuclear power plant, and you can use that to make neutrinos, because that's part of what's happening. We can collide particles together, and when they decay, they create a whole bunch of different things, but one of the things they create is neutrinos. And so you can actually make a beam of neutrinos with a particle accelerator. And in fact, this is how we found out that they change flavors, because the mine that I was in, the neutrino detector in Minnesota, partnered up with the particle accelerator Fermilab in Chicago. And what Fermilab did was they created a beam of neutrinos with their particle accelerator of one specific type, because they could create what type of particles are going to interact. So they created this beam of neutrinos of one type, and they beamed it to this mine in Minnesota through the Earth. So you have the curvature of the Earth, and here's Chicago, and then here's the mine in northern Minnesota. And they beamed this beam of neutrinos through the Earth to the detector in the mine. And they were only creating one type of neutrino. And what they found was multiple types of neutrinos, which meant that they were changing flavor. So we can prove that they change flavor. We don't know why they change flavor, but we can prove that they do. So we can see them in any type of nuclear interactions. That's where neutrinos come out of. And so one of the ways that we can detect neutrinos is we can detect neutrinos from the sun, because for a long time we didn't know how the sun produced all of its energy. How can it shine as a star for billions of years? And in the 50s, we found out that there was nuclear fission and nuclear fusion. And so the idea was, well, if you crush hydrogen enough under enough gravitational weight, the hydrogen will start fusing into helium, and that will produce the energy to keep the sun bright. And that was the solution for how the sun kept shining. But of course, you couldn't prove it. You can't go to the sun and see nuclear fusion. And at the time, you couldn't create nuclear fusion on Earth. And so how do you prove that the sun is actually fusing hydrogen into helium? Well, it turns out when they had the first neutrino detector, they could actually detect the neutrinos that were coming from the sun. So inside the core of the sun, all of these hydrogen atoms are fusing into helium atoms and other things. And one of the byproducts is neutrinos. And the neutrinos, since they don't pass through anything, they don't collide with things very much. As soon as they're produced, they basically just leave the sun and stream out in all directions. And so then one of the directions it would find is the Earth. And so you'd have this neutrino detector buried half a mile underground, and it would be able to detect this bright beam of neutrinos coming from the sun. And so we can see what are called solar neutrinos that are caused by the sun. And it was the first proof that nuclear reaction was happening inside the sun. And it even started a bit of a controversy, because at the time they did the basic math of saying, okay, the sun is this hot, it produces this much energy, so therefore it must be fusing this much hydrogen per second. Basic calculation that you can do. And and that means that you would get a certain number of neutrinos produced every second. Well, when the neutrino detector went on, it found a third of the neutrinos that it should have seen. So it should have seen 3 times more neutrinos, according to the calculations for the sun, than it was actually seeing. And for a long time, we couldn't figure out what this is. Like, how is it not producing enough neutrinos? Are we not seeing them, or is the sun fusing less matter than we thought it was? What's going on? Well, it turns out that there are 3 flavors of neutrinos, and the sun was producing one type of neutrino, one flavor of neutrino. And when it came to the Earth, it was switching back and forth between the different flavors. So by the time it reached the detector, it was spread out over 3 different types, just randomly 3 different types. So we were only seeing a third of them. We were only seeing the ones that were still the same type. The other 2/3 that were the other 2 types, we couldn't see. And so by finding out that the neutrinos could change flavor, we solved the mystery of why solar neutrinos were so weak. So that's one of the big things that we've been able to do with neutrinos. Another one is in 1987, there was an odd thing where these neutrino detectors were doing their little experiments, and two of the neutrino detectors, one in Europe and one in the United States, got a neutrino spike. And I thought, well, that's odd. Why would we get a neutrino spike? Well, it turned out that evening, a supernova was detected in the southern hemisphere. And what had happened was, when a supernova occurs, a supernova is caused when a star dies. Basically, a large star is creating all this fusion heat to keep itself from collapsing. And when it starts running out of hydrogen, it starts fusing helium into carbon, and then to nitrogen, and then oxygen, and then keeps going and going, and just keeps fusing heavier and heavier elements to try and keep itself from collapsing. And eventually it fuses all the way up to iron. And the interesting thing about iron is that you can fuse from iron to heavier elements, but if you do it, you don't get extra energy, you lose energy. So what happens is it fuses all the way up to iron, and then it tries to fuse elements heavier than iron, and that takes away energy. So it's like turning on the freezer, and the entire core of the star collapses, and all those iron atoms slam together, and they bounce back, and it rips the star apart in what we call a supernova. So the entire star explodes in this supernova. Well, one of the things that happens is when the iron atoms collapse, they are fusing into heavier elements. So any element on the periodic table that is heavier than iron is actually created in things like supernova. So things like gold and silver and things like that, those are created in supernova. And that's why we have them here on Earth, because long before the Earth formed, these stars died as supernovas, and then the sun and the Earth formed out of the gas and stuff that was left over from the supernovas. So when that happens, when those heavy elements fuse, you get a burst of neutrinos. And the thing is that when that matter collapses and it fuses, it pushes out, but it has to push all the other outer layers out. So we don't see the supernova yet. But the neutrinos, they were formed and they just go zip right out of the star. So they reach the Earth first, because they just leave the star, and then we get this burst of neutrinos, and then we can see the supernova, because by that point, the star has started to rip itself apart. So the neutrinos that we found this spike of neutrinos in 1987. That was actually the first neutrinos that we have ever observed from outside the solar system. And it came from a supernova that was actually in one of the Magellanic clouds. It came from outside the Milky Way. So it was, 200,000 light years away, and we could still see that burst of neutrinos before the supernova. So that was the idea, that we could see, yes, when stars go supernova, they do create all these heavy elements, because we could see the neutrinos. And we could say, well, we think that's how the star works, but because we're detecting the neutrinos from the supernova, then we know that that's how they're working, because those neutrinos were produced by the supernova. So one of the big things now is in Antarctica, because it's very remote and because it has a very sensitive detector, they've been able to detect neutrinos from outside the solar system. What they are really trying to do is find the signature neutrinos from the Big Bang. So as you can imagine, when the Big Bang started everything and created all this matter and energy, most of the neutrinos that are streaming through your body should be from the Big Bang, but they're hard to detect. And so as they're doing these studies, looking for these cosmic neutrinos, they've sometimes found really high energy neutrinos. like neutrinos that have so much energy, they just kind of slam through things. They get this little spike of a signal. And we're still not entirely sure what causes them because they're just really, really, really high energy. But there was a recent study that actually was published this year that seems to look at whenever you get one of these bursts of high energy neutrinos, you also get a radio flare from distant objects called quasars. Quasars are supermassive black holes in the center of galaxies, and they produce so much energy and they're so far away. They look like little points of light because even though they're bigger than our solar system, they are billions of light years away. And quasar actually stands for quasi-stellar object, quasars. And they were first seen as like points of radio light in the night sky. So what we could see is that when we get these bursts of neutrinos, we're getting a flare up in one of these quasars. So quasars flare up when there's nearby material that's being eaten by the black hole. So what it seems like is that these really high energy neutrinos are being produced when matter is being consumed by a black hole. It gets so hot and so under so much pressure that it creates these really, really high energy neutrinos. And so not only are we using neutrinos to study stars and to study supernova, but now we may be using neutrinos to study black holes. And the reason we can do them is because neutrinos basically go through everything. They aren't affected by much. So that's kind of the big thing in terms of modern astronomy. Now, I guess one last thing that's interesting about neutrinos is that there's another property of neutrinos that is sometimes called helicity or handedness. And it has to do with the fact that elementary particles, basic particles, have this property that's like rotation. We call it spin. It's kind of like a little spinning top, except that a top is made up of a whole bunch of different atoms swirling around, you know. These are just an elementary particle, and they just have this little spin to them. Well, neutrinos are elementary particles, and so they have a spin to them. And that means that when a neutrino is traveling through space, its spin can either be in one direction as it travels or in the other direction as it travels. In other words, as you see it traveling along a path, it can either go clockwise or it can go counterclockwise. And that's what that helicity is. It's either left or right. It's either clockwise or counterclockwise. Well, it turns out that the neutrinos that are produced all have the same helicity. They all, when they're produced, they all travel with the same handedness. They're all left-handed. And we don't know why, but all of them are. So every other elementary particle can be right-handed or left-handed. So why are neutrinos only left-handed? Well, one of the theories that's out there is that, well, maybe there are ones that are right-handed, but they wouldn't interact with regular matter at all. They would still have mass, they would still be out there streaming through space, but they would only interact gravitationally. And because they wouldn't interact with regular matter, they would be called sterile neutrinos, neutrinos that don't interact and don't produce other things, so they're sterile. Well, one of the ideas is that if sterile neutrinos exist, then they would be very different from regular neutrinos. And since they wouldn't interact with regular matter, they could be what we call dark matter. And so there's these other handed neutrinos that have mass and don't interact with regular matter, so we wouldn't see them, but we would see their mass, we would see their gravity, and they would tend to clump around galaxies and create what we would call dark matter. So one of the ideas to explain dark matter would be these other types of neutrinos. So neutrinos might solve the mystery of dark matter, but we don't know yet because we can't interact with them. So it's one of those things where neutrinos are very strange. We've known them for less than 100 years, and they are one of the most powerful tools we have for understanding really high energy things in the universe. So is that explain enough? Have I
No, explained very well.
bruised your brains enough?
No, wow. Well, yeah. But, yeah, great.
That'd be
though.
great if it did
Yeah.
unlock the mystery of dark matter.
That is one of those things that it keeps coming up again and again as well. Maybe it possibly could, maybe it couldn't. Dark matter is one of these strange things because we can't fit it into our standard models of things. And as we keep testing new ideas, we keep getting proven wrong. So basically we know, well, dark matter's not that, and it's not this,
Okay.
and it's not this. So
That's science. That's what
that's
science
science.
does.
That's how it works. That's right.
Yeah.
So we know what it's not, but we don't necessarily know what it is.
Cool.
Yeah.
Yeah.
Good. Interesting.
Yeah.
Okay. Well,
Great.
We loved it.
very good.
Always.
Yep.
I will
Thanks,
try
Brian.
and think of something next week, and I will
We'll keep going.
I will talk to you then.
Great.
We'll be right here.
Okay.
Thank you.
Thank you.
Thanks.
Okay.
Bye.
Bye.